So before we move on to section 3, we're going to do this section 2.5, where we talk about tree diagrams, permutations, and combinations. So a tree diagram helps us display the outcomes of an experiment consisting of a series of outcomes. So it's more useful if you have a lot of, like, if you're going to do conditional probability, it's very useful for that. And if you obviously have multiple events. So the best way to kind of talk about tree diagrams is through an example. So YouTube is a popular destination on the internet for video sharing. About 27% of adult internet users are 18 to 29-year-olds. Another 45% are 30 to 49 years old, and the remaining 28% are 50 and over. A study done found 70% of internet users aged 18 to 29 have visited YouTube. 51% of those ages 30 to 49, and 26% of those 50 or older. Draw a tree diagram to represent this situation. So the first thing we want to do is, so we start with our population is adult internet users. And based off that, we have 3 categories that we're looking at. 18 to 29 years old, 30 to 49 years old, and 50 and over. Okay, so now we want to talk about the percentages that are in each of these categories. So 27%, so we use the lines to denote that. And then 30 to 49 is 0.45, and 70% are 50 and over. Sorry, 28%. Okay, so because these are our only 3 categories, those percentages have to add to 1, so 100%, and just double checking, they do. Okay, now within each of those age groups, we have either they visit YouTube or they don't. So visits YouTube, doesn't visit YouTube. Okay. For our 18 to 29-year-olds, 70% visit YouTube, which means 30% don't. So of our subcategories, those also for each, in this case, age group would have to add to 100%. So then for our 30 to 49-year-olds, we have visits YouTube, doesn't visit YouTube. And then we know 51 have visited, which means 49 haven't. And then our 50 and over, same thing. And we have that 26% visit, which means 74% don't. And we'll talk in a little bit, we're going to do examples next on how we find probabilities based off our tree diagram. Okay, so we're selecting an adult internet user at random. We want the probability that this person is 18 to 29 and visits YouTube. Okay, so on a tree diagram, to find and, what we do is we multiply the branches. So in this case, probability you're 18 to 29 and visit YouTube. So 18 to 29, 0.27, and YouTube, 0.7. So we do 0.27 times 0.7, and we're going to get 0.189. Okay. Next, we want to find the probability the person has visited YouTube. So that is probability you're 18 to 29 and visit YouTube, probability you're 30 to 49 and visit YouTube, and then the probability you're 50 and over and visit YouTube. So we're going to have to do a lot of multiplying. So 0.27 times 0.7 plus 0.45 times 0.51, and then 0.28 times 0.26. So we end up getting 0.4913. Okay. The last is, given that a person has visited YouTube, what is the probability that he or she is age 30 to 49? So this is the probability you're 30 to 49 given you visit YouTube. So what we want to do is the probability you're 30 to 49 and visit YouTube divided by the probability you visit YouTube. So the nice thing is we have found the probability you visit YouTube, which takes part of the work out of the problem for us. So first in the numerator we need probability the 30 to 49 and visit YouTube. So that's going to be 0.45 times 0.51. And the probability you visit YouTube, we found in the previous example, we know is 0.4913. So we're going to do 0.45 times 0.51. And we get 0.2295. We divide by 0.4913. And we get 0.4671. So in a couple important things to remember about tree diagrams, each branch adds to 100%. And then it's just multiplying those branches to find ands, which is the two main important things for a tree diagram. Okay, so let's look at another example. So in a recent month, 88% of automobile drivers filled their vehicles with regular gasoline, 2% purchases mid-grade, and the rest bought premium. Of those who bought regular gas, 28% paid with a credit card. Of customers who bought mid-grade and premium, 34% and 42% respectively paid with a credit card. Suppose we select a customer at random. So we start with people who have filled car with gas. Okay, so we have three different types of gas. We have regular, mid-grade, and premium. So we know 88% bought regular, 2% bought mid-grade, and the rest were premium. So regular and mid-grade get us to 90%, and the rest have to add to 100, so 0.10. Okay. For each type of gasoline, we either have that they used a credit card or not. So if you bought regular gas, 28% paid with a credit card, which means 72 did not. For mid-grade, 34% paid with a credit card, which means 66% did not. And then for premium, 42% paid with a credit card and 58% did not. Okay. I'm going to go ahead and find all of the and probabilities now, just so I don't have to do it later. So regular and credit is 0.88 times 0.28. So that's 0.2464. Regular and not a credit card, 0.88 times 0.72. It's 0.6336. Mid-grade and credit card is 0.068. Mid-grade and not a credit card is 0.0132. Premium and credit is 0.1 times 0.42, so 0.042. And then premium and not a credit card, 0.10 times 0.58, which is 0.058. This just makes it easier so that later I don't have to do a bunch of multiplying. I can just do it now. So one other thing is when I find all of the ands, all of these percentages will also add to 1. So now find the probability that the customer paid with a credit card. So if we're looking through, I went ahead and found all my ands. So this percentage, the 0.2464, 0.0068, and 0.042 all come from buying the type of gasoline and paying with a credit card. So 0.2464 plus 0.0068 plus 0.042. And we get 0.2952. Next, given that the customer paid with a credit card, find the probability that she bought premium gas. Show your work. So this is the probability of buying premium given you paid with a credit card. So we're going to do the probability of premium and credit over the probability of credit. So premium and credit is 0.042, and we just found the probability that you pay with a credit card, 0.2952. So we get 0.1423. A lot of the time, when you get to the problems where you do givens with these, you're not going to get nice decimals. So as long as you give me a minimum of 3 decimal places, I'm fine. 4 decimals is preferred, but at a minimum, you have to give me 3. Okay, so tree diagrams, just a couple things, tell us how many possible outcomes there are and help us list those individual outcomes and organize the probabilities associated with each stage. So like we've known in the previous 2 examples, we've had 6 outcomes, depending on either your age and whether or not you visit YouTube or not, and depending on what type of gas you fill your car with and whether or not you pay with a credit card. However, if we're only interested in the number of different outcomes created by a series of events, we're going to use something called the multiplication rule of counting. So these were probabilities associated with each outcome, where instead of we can just say, all right, what's all of the different possible outcomes we can do? So if there are n possible outcomes for an event and m possible outcomes for a second event, then there are a total of n times m possible outcomes for the series of the two events. And it just increases then on if you have more and more events. So like I knew there were 3 different age categories and 2 different categories further. So 3 times 2 gave me my 6 outcomes. Works the same way with the gas. We knew there were 3 different types of gas. There were 2 payment options. 3 times 2 gives us 6. So there are 31 different sandwich options at McDonald's, not including breakfast. You have 4 different size options for fries, small, medium, large, and super, and 4 different size options for drinks, same 4 sizes. How many different meals can be ordered from these options from McDonald's? So first category has 31 options times the second, which for drinks, which is 4, times the third, fries, and then drinks. So 31 times 4 times 4 gives us 496 different meals, and that's not including breakfast. So lots of different meals. You could go more than a full year without having the same meal twice, including size options for fries and drinks. But when we have those n items, sometimes we need to know the different number of ordered arrangements. So in the previous example, it didn't matter what you ordered first, but in some cases, the order does matter. So a classic example of this is the number of different ways in which 5 people can be seated at the dinner table. So the first person has all 5 seats to choose from. But once that person sits down, the second person only has 4 seats to choose from. The third person has 3 seats to choose, so on and so forth. So we're thinking in terms of that, we have 5 times 4 times 3 times 2 times 1, which gives us 120 different seating options. So this is not unusual. So this is where we have something called factorial. So it's that lovely exclamation point in mathematics. It's read as factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So, and then just a couple general pieces of information. 0 factorial is 1, and 1 factorial is 1. We're not going to have to deal with those very often, but it's just a piece of information. So, back to our dinner party. We've invited 5 people, but we only have 3 chairs. How many ways can 3 of the 5 people seat themselves in the chairs? So when we think of this, the first chair has 5 choices. The second person has 4 choices, and then our last third person has 3 chances. 3 choices. So 5 times 4 times 3, which is 60 different arrangements. Okay. So this could get very complicated if you have lots of options, like if your sample size gets bigger and the different options. So when the order of something matters, it's called a permutation. And we use the notation NPR, and there is a formula that we use to find it. But I'm also going to show you how you can get to it on your calculator. So if you hit math, then you go over to PRB, and then you want number 2. So we use a permutation when order matters when we're looking at the number of arrangements. We'll look at it here in a second when order doesn't matter, and see how that changes. So doing what we just did, where order matters, we have N is the total number. R is how many you're taking. So when we had 5 people to sit in 3 chairs, N is 5, R is 3. So we're doing 5PR, which if we're doing the formula is 5 factorial over 5 minus 3 factorial, which we can plug into the calculator, 5 and 3, and then we hit enter, and it will give us 60. I do not require that you memorize the formula. You are more than welcome to use the calculator function every time. Okay. So far we've talked about how the order of people matter. Okay, so basically it's saying we're looking at different groupings of 5 people, but sometimes order doesn't matter. So we just want 3 people. So we were looking at different groupings of 5 people so that each group contains 3 people. It doesn't matter the order in which those people sit down. It changes. So the way the formula changes is, so we have the 5 factorial, but so like all of the different orderings of like the 3 people count as the same event. So like if you have 3 people, person A, B, and C, all of the different ways those 3 people sit count as a single event. So there are repeated events. So that's where we get 3 factorial times 2 factorial, which only gives us 10 combinations. Okay. So since order doesn't matter here, the number of combinations is a lot smaller because the A, B, and C are 3 people of them sitting. Those 3 people sitting in any combination of the 3 seats is considered the same event. So when NCR, which we usually read as N choose R, is what we use for combinations when the order doesn't matter. So it's N factorial over R factorial times N minus R factorial, which again, memorizing the formula not super important. You can get to this by going to math, PRB, and then number 3. So order does not matter in finding the probability. So when you're trying to figure out if you need to use a permutation or a combination, the first thing you need to ask yourself, does order matter? If the order does matter, you're going to use a permutation. So a couple things are always going to be a permutation. One of those if you're placing people. So that means first place, second place, third place. That's always going to be a permutation. Also, if you're doing something where you have a president, a vice president, a secretary, a treasurer, stuff like that, that's always going to be a permutation. Some things are always permutations. There's a lot of different things that can be examples of a combination, so I'm not really going to go over over examples of those. But those are a couple different examples of when you'll always use permutations. So like we kind of already talked about, permutations and combinations determine the number of different outcomes in your sample space. They don't find probabilities. We will eventually talk about probabilities a little bit, but for right now, we're just going to talk about how to calculate combinations and permutations. So the last thing we need to touch on is with and without replacement. So we mentioned this briefly earlier, is the with and without replacement. So when the probability of an event happening changes based on a previous outcome, it's usually because of something called without replacement. So anytime you're pulling something out of the bag and you're not putting it back, like marbles or, candy, that's usually called without replacement. If you're drawing a card from a deck of cards and you're not putting it back, that's without replacement. So if something can only be selected once, that's sampling without replacement. If it can be selected more than one time, we are sampling with replacement. So for example, in your dresser drawer, you have apparently just thrown your socks about willy-nilly and you don't pair them up. And you've got 6 blue socks, 10 gray socks, and 4 black socks. You decide to get dressed in the dark and you just grab 2 socks from the drawer. So this is obviously without replacement. And we want to know the probability that both socks match. So there's 3 different colors of socks, which means there's 3 different probabilities we're going to look at. So there's the probability both socks are blue, there's the probability that both socks are gray, and there's the probability that both socks are black. Any of those 3 outcomes could happen, and we'd add them all together to get the overall probability. So we have the probability of blue and blue plus the probability of gray and gray plus the probability of black and black. So the probability that the first sock is blue, well, we have 6 blue socks. And if we add up all of our socks, we get 20. So 6 out of the 20 socks are blue. Multiply it by the probability that my second sock is blue. Well, assuming the first sock is already blue, there's now only 5 blue socks remaining. And there's only a total of 19 socks remaining. So both the numerator and the denominator have decreased. Okay. Now we move on to gray. So 10 out of the 20 socks are gray. So the probability of the first sock is gray times, and then the second sock, there would be 9 out of 19. And then lastly, 2 black socks. So 4 out of 20 times 3 out of 19. So we're going to multiply our probabilities together, add them up, and we're going to end up with 0.347. So not a great probability that you grab 2 pairs of matching socks, but it's not bad either. We could also do a comparative here. Like I want to know, well, which pair am I, or what color has the highest probability of being drawn, like matching sock wise? It's going to be gray because that's the most of the socks are gray, so it has the highest probability of happening. You could do any combination of the 2 colors, like what's the probability I get a blue sock and a gray sock, so 6 out of 20 times 10 out of 19. So there could be ways you do the probabilities where only the denominator changes if you're looking at 2 different, in this case, color socks. We're going to take a look at more examples of probability with and without replacement. In class, we're going to do some more examples. So if you're not quite comfortable with it or tree diagram, we're going to be doing more practice with it in class. So let me know if you have any other questions.